We can now move on to section 2.4, which is arc length of a curve, and surface area. So arc length of a curve, I'm going to show you where they get this from. I don't want you just to have to remember it. I want to show you actually where we got it from. And so this is how I'm going to show you. So first of all, what I mean by the length. So if I have a curve, that's a horrible line, but y'all get it. If I have a curve, what I mean is from A, let's just put A here, to B, let's put B here. I want to know what the length of this arc is. So what is the length of this curve here? That's what I want to know. So to show you where they got it from, I'm going to pretend like I'm zooming in. Okay, so I'm going to like take this and pretend like I'm zooming in to just a tiny spot. If I zoom in really close, it's going to look like a straight line. Okay, so I'm going to use a straight line to show you this. So let's say I want to find the length of a straight line. Okay, well, notice I can make a right triangle out of this, where my height is the change in the y, right? My change in y. And my length is going to be my change in the x. So to figure out how long my length is, we can use the Pythagorean theorem and find it's the square root of each of these squared. So dx squared plus dy squared. So from that, I can gather that my length is equal to the square root of dx squared plus dy squared. Now this is nice, but it's not super helpful. But remember, dy over dx is my slope, which is also in this class known as the derivative. So if I could get this in terms of dy over dx, I can factor in my derivative. Okay, so to do that, I'm going to, out of each of these, factor out a dx squared. So that's going to give me x squared. If I factored that out of the first part right here, well, all I had there was dx squared. So that's just going to leave me with a 1 plus, now I can divide this by dx squared. So dy squared over dx squared. Now, since this is a square inside of a square root, I can bring it out and get rid of the square. So that's going to be dx square root of 1 plus, both of these are squared, so I can write it as dy over dx squared. Well, what dy over dx is, as we learned in Cal 1, that is the derivative. That's where they get our length from. Okay, so the arc length is going to be equal the integral from a to b of the square root of 1 plus the derivative squared. And it works the same way if it is in terms of the y. So now let's practice this. I'm going to actually, just as a heads up, I'm omitting example number 3. If you plugged it into the formula, it gets to a part we can't actually do yet, but we are going to get there. Just where we have gotten to in the book. As of now, we can't do it yet. So omit that one. We are just going to do 1 and 2. And I'm going to use these. So example number 1, let f of x be equal to 2x to the 3 halves. Calculate the arc length of this from 0 to 1. So I want to plug it into the formula. Notice what I need out of the formula is the derivative. So we have to find the derivative. This is a Cal 1 skill, right? So remember, for the derivative, I'm going to bring my power down, so 2 stays there. Bring my power down front, which is going to make it 3 halves, times x, and I'm going to decrease my power by a 1. 3 halves minus 1 is equal to 1 half. So my new power is 1 half. 2 over 2 cancels out, so I'm left with just 3x to the 1 half, which is like saying 3 square root of x. If you would rather write it like that, it doesn't really matter. Make sure you know how to find that derivative. If not, let me know. Can help you out. So now I can plug it into the formula for length. Length is going to be equal to the integral from a to b, and this one it's saying from 0 to 1, so 0 to 1 of the square root of 1 plus the derivative squared. The derivative is 3 square root of x. Excuse me. So now we can work that out. So this is going to be integral from 0 to 1 of the square root of 1 plus 3 squared is 9. Square root of x squared is x dx. This is actually something we learned in Cal 1. I say we, it might have just been you. You may not have had me for that class, but if so, we did this in Cal 1. This is called U substitution. So I'm going to let u be equal to the stuff inside of the square root. And the reason I want to do this is because there's not a clean and clear way to solve this. But if this was just square root of u, then I could, because I could then make this u to the 1/2 and then do it like we have been doing. But since this is the square root of a bunch of stuff, I don't want this stuff here, right? So I make it the square root of, so I make u equal to 1 plus 9x so that I just have a u in here. But I have to make sure the derivative of that is there, right? So the derivative of u is just 9, right? The derivative of 1 plus 9x is just 9. So I have to make sure there's a 9 here. But there's not. But that's okay, because I can put a 9 there as long as I put a 1/9 out front. So this becomes 1/9 integral. The bounds I already had were bounds for the x. I need them in terms of a u. So if x was equal to 0, u would be equal to 1 plus 9 times that x, which is just giving me 1. So my bottom bound is now 1. My top bound was originally 1, but the u would be 1 plus 9 times that, so times 1. 9 times 1 is 9, plus 1 is 10. So my upper bound is 10. Square root, this becomes a u, so I can just write that as u to the 1/2 du. I have a video over u substitution I will link to as a review for this stuff. So now I could just take the antiderivative, 1/9, add 1 would give you to the 3/2 over 3/2 from 1 to 10, which is like saying times 2/3. 1/9 times 2/3 is 2/27. So 2 over 27 times 10 to the 3/2 minus 1 to the 3/2. Now remember I said that a power of 3/2 is like doing the square root first, but notice there is no rational square root of 10, so it's okay just to leave this here. Okay, so you can just leave it as 10 to the 3/2. That's perfectly fine. Again, because I would normally do the square root first, but there's no rational square root, and so I'm just going to leave it here. But 1 to the 3/2 is 1, so you can go ahead and put that. It's perfectly fine to stop right here. I'm fine with that. I'm not trying to make sure you know how to do 10 to the 3/2. I don't care about that. Stopping here is great. So once again, let me know if any of that does not make sense as we move on to example number 2. Same thing, let f of x be equal to 4/3 times x to the 3/2. Calculate the arc length of the graph from 0 to 1. So we're going to do the same thing. First thing I need is the derivative. So the constant out front is going to stay, so 4/3 is going to stay out front, taking the derivative. Again, because I need it for this, right? 4/3 is going to stay out front. I'm going to bring my power down, so bring the 3/2 down. X to the power of, decrease it by a 1. 3/2 minus 1 is 1/2. 3's cancel out here. 4 over 2 is just 2, so we get 2 square root of x. And then do this the same way. So the length is going to be equal to the integral. My bounds here are 0 to 1 of the square root of 1 plus the derivative squared. So just like we did on the last one, this is 1 plus 2 squared is 4, square root of x squared is x dx. I don't want stuff in here. I just want it to be a one term, so I want this just to be a u. So let u be equal to 1 plus 4x. So the derivative of that is 4. I've got to make sure I have a 4 in here, but I can't just put a 4 there. I have to also put 1/4 out front. So that's going to make this 1/4 integral. Plug 0 into the u, so that would just be 1. Plug 1 into the u2, so 1 plus 4 is going to be 5. Square root of u would just be u to the 1/2 du. Take the antiderivative, would be u to the 3/2 over 3/2, just like on our last one. I can multiply this by 2/3 instead. 1/4 times 2/3 gives you 1/6. So out front we're going to have 1/6 u to the 3/2 from 1 to 5. Plug in 5 first. 5 to the 3/2, I would do the square root of 5 first, but that's not a thing, so you can just leave it. That's 5 to the 3/2 minus, plug in a 1. 1 to the 3/2 is just 1. And it's perfectly fine, once again, just to stop right there, because 5 to the 3/2 isn't a rational thing. Okay. So now I can use the arc length to find the surface area of a solid. So this kind of adds to what we did our last class. So the surface means the outermost part, right? Remember I had this cup and I showed y'all with the cup. I'm taking the outermost part and I'm going to lay it down flat, right? So just like it was our last class, that shape I'm going to lay out flat is a rectangle. Now, last class, we said this was just 2 pi and then the x, right? The reason I said x was because that was my length, right? However, now I know how to find my length over a certain amount of time, right? So I'm going to use this length instead. So now this is going to be square root of 1 plus the derivative. This is still my function. So this time, the area of this place in here, which is what I want, is going to be 2 pi integral from my bounds of f of x times my arc length, which is where they get this from. And again, it also works in place of the y. Sorry, this should have been the derivative squared. That's where they get this from. It's my length times my height, and my height is going to be the function. So, example number 4, let f of x be equal to the square root of x from 1 to 4. Find the surface area of the surface we make by revolving the graph of f of x around the x. Oh, and then a note I put right here, the variable inside has to match what I rotate it by. So if it's in terms of x, I've got to rotate it around x. If it's in terms of y, rotate it around y. So, for example number 4, first thing I need is the derivative. Remember, the function is square root of x, for example number 4. And as we learned in Cal 1, since that's like saying x to the 1/2, the derivative, bring the 1/2 down front, x to the power of, decrease it by a 1. 1/2 minus 1 is negative 1/2. So this is 1 over 2. X to the 1/2 is like saying the square root of x. So the derivative of the square root of x is 1 over 2 square root of x. So this means the surface area is going to be equal to 2 pi integral. My bounds here are 1 to 4. The function first, so square root of x times the arc length. So square root of 1 plus the derivative, which is 1 over 2 square root of x squared dx. Now this is another thing people always get scared because this looks hard, but it's not. Watch it work out really nicely. So this is going to be 2 pi integral 1 to 4 square root of x times the square root of 1 plus 1 squared is 1 over 2 squared is 4 square root of x squared is x. Now, a lot of people get here and they say, I'm stuck, I don't know what I do next. Well, notice here, this is a square root times a square root. So since they're both under a square root, I can distribute this x through this whole thing. So this becomes 2 pi integral 1 to 4 of the square root of x times 1 is x. X times 1 over 4x, the x's cancel out, and I'm left with just 1/4. So now this is just like what we did on examples number 1 and 2. I can let u be equal to x plus 1 over 4. So du has to be 1 dx. Luckily, I pretty much already have a 1 right here, right? Because everything has an imaginary 1, right? So this becomes 2 pi integral. My bound was a 1, but if I plug in a 1 right here, 1 plus 1/4 is going to be 5/4. 4 plus 1/4 is going to be 17/4. Square root of u is u to the 1/2 du. Antiderivative, as we saw on examples number 1 and 2, the antiderivative of u to the 1/2 is 2/3 u to the 3/2, from 5 over 4 to 17 over 4. Plug in our top bound. If you want to, 2 pi times 2/3 is 4 pi over 3. You don't have to, though, that's fine. 17 over 4 to the 3/2 minus 5 over 4 to the 3/2. This is not a rational number, so you can just stop there. Once again, if any of that isn't making sense, please let me know. I will happily help out. One more example, example number 5. Let f of x be equal to the cube root of 3x. Consider the portion of the curve where y is between 0 and 2. Find the surface area found whenever I rotate that around the y. So here lies our problem. This is in terms of x rotating around the y. So what this means is I have to transform this to be in terms of y since it's being rotated around the y. Because of this note here, they've got to match, right? So I need this to be in terms of a y since I'm rotating around y. So let's start with that. So I know y is equal to the cube root of 3x. So in order to make this in terms of, sorry, this is example 5. To make this in terms of a y, I'm going to have to solve this for x. So first things first, I have a cube root, which means I'm going to cube both sides. So y cubed equals 3x, and then to solve it for the x, just to divide it by 3. So the function in terms of y is going to be y cubed over 3. That's what I want to use. So now I can use this. First thing I need is the derivative of y. Bring down our 3, right? But 3 over 3 is just a 1, so that's nice. And then decrease that by 1, just gives us y squared. So the derivative is y squared. So surface area is going to be 2 pi integral. My bounds are from 0 to 2. So 0 to 2. The function goes out front, so that's y cubed over 3 times the arc length, 1 plus the derivative squared. Let's simplify this because it looks like a mess. Over 3 is a constant, so I can bring that out front. So 2 pi over 3, integral from 0 to 2, y cubed, square root of 1 plus y squared squared is y to the 4th. Now the difference here is on my last one, I had a square root right here, right? So I could make this one term. This doesn't have a square root, so that doesn't work. But notice the whole thing is I want a u in here, right? So I can let u be equal to 1 plus y to the 4th. And the derivative of that, bring the 4 down, is 4y cubed. And what's awesome is I already have y cubed right here. So that's really nice. So all I need is the 4. In order to put a 4 in there, I need to put a 1/4 out here. And now I can move on. 2 over 4 leaves me with a 2. So out front I have pi over 6. Integral 0 plug 0 in here, and my new bound is 1 plus 0, which is 1. Plug in a 2, 1 plus 2 to the 4th. 2 to the 4th is 16. 16 plus 1 is 17. Square root of u is just u to the 1/2. As we have now seen many times, the antiderivative of u to the 1/2 is 2/3 u to the 3/2 from 1 to 17. Pi over 6 times 2 over 3. I can cancel out 2's here, leaving me with 3. So I get pi over 9 times 17 to the 3/2 minus 1 to the 3/2, which is just 1. 17 to the 3/2 is not a rational thing, so we can just leave it there. And that's what I get. So once again, don't let the numbers scare you here. This isn't as hard as you would think it is. But of course, if it doesn't make sense or if you need any help at all, just let me know.